So there are two ways to map out an area. You can use a square grid or a circular polar type grid. Now, no one, as I've stated in my previous video, no one ever said I'm going to survey my property, my state, my country, my continent in the form of a globe so I know where everything is. Everything is laid out on a flat plane so that you know where everything's at. Because on a square grid, wherever the lines intersect, and you can create as many divisible lines as you need, wherever the lines intersect it would be a point on the map of land or a point of interest. And the same thing for the circular or polar version. So if you were to just put that over the grid, either one, wherever the lines intersect would be a point you would mark on the map. So if there's a point right here, let's just draw something let's just draw that right there. So regardless of which map or mapping you do, as long as you kept that map in that form and your center point was the same, you would know based on the center point of where you're at, the location based on degrees or intersecting lines, where that point is. So if you transfer that into a small version or replicated it, you would always know based on the center point of where that center point is, where everything else is at. The problem lies in that once you created the map in that form, if you change either one, it would distort the relative size and location of that point. So if you took the square and converted that into a polar region, it would distort it. And the same for the polar region. If you took the original polar region and converted it into the square type map, it would distort it. So once it's created, it has to stay in that format if that's what you're using. So the whole idea of projections makes no sense because every projection will distort something. So we have to understand that the only way to map it is on either a square or a circular map. The question is why a circular map was used and is still being used today. And that's very interesting because, well, it's not, sadly, I was going to say sadly, but unfortunately, we are not taught the reasons for that, why there's a circle, and more specifically, why there's 360 degrees of a circle. Why every circle is always considered to have 360 degrees. You could have whatever you wanted. You could divide that into 800, 700, 1,000 degrees. Why is it 360 degrees? So let's see what the Ministry of Truth website has to say about why a circle has 360 degrees. The original, well, let's highlight this here so you can know what I'm talking about. The original motivation for choosing the degree as a unit of rotations and angles is unknown. One theory states that it is related to the fact that 360 is approximate number of days in a year. Ancient astronomers noticed that the sun, which follows the ecliptic path over the course of the year, seems to advance in its path by approximately 1 degree each day. Some ancient calendars, such as the Persian calendar, use 360 days for a year. The use of a calendar with 360 days may be related to the use of sexagesimal numbers. Ooh, butchered that one. The answer is all right there. Now you have to understand that a good lie always has truth mixed in. And that is exactly what happened with the circle, with this topic right here. So what happened is the ancients, whoever they were, realized that the sun took approximately 360 days to return to its original location because the sun is always moving. So what I did is I took the timeanddate.com snapshot for 1 day on the first of the month for 12 months. So this is a series of 12 images. So the sun, here's GMT line right here. Okay, so GMT midnight, so it's midnight in England, and it's noontime on the other side. So watch as every month, if I go back, or now the sun is actually starting to watch as it goes. This is April, May, June, July, August, September, October, November, December. And then it goes right back to. Now watch it in motion. Notice the figure 8. So the ancients found out that the sun's gyrations always return back to its original position every 360 days, roughly. We know now it's more like 365 if you average it out, but for them it was figured 360 days. That's how we wound up with 360 degrees. Now, if it was wrong, would they still be using that? Of course not. Because that is why the Earth is always mapped in a circle. Because the sun going around the circle is what dictates the map. That's why it's a circle. That's why we don't use a square. It's because the sun, and I'm going to show you this in a little bit here too, the sun rotating around the Earth dictated which map to use. Okay, so let's say you found Hawaii and you wanted to map it out. And we're going to put a center point in that area. That's your home base. And we're going to put a circle in degrees, 360 degree circle on there. Now, we're going to start rowing out to each island And as each degree you pass, you're going to start marking it, both longitude and latitude. Now, when you get done and you mapped all that out to all the islands, would that not be an accurate representation and size of the islands in respect to the center point? Of course it would be. The size and the location of the islands would be correct. It would be an accurate representation of reality on that map. So here's the latest update on the azimuthal equidistant map we've come to know as the Gleason map. Now, turns out the equidistant, well, that part we probably kind of knew, was the latitude lines are all equal distant from the center outward as far as it'll go. Well, it turns out and it makes sense, there'll be a point from the inside to the outside where one of those degree lines of longitude will be equal to the latitude. And it turns out that part is the equator, hence the name. So the equator is named that apparently because at that point it is equal distant to the latitude lines. That is why when I did the calculation on the speed of the sun, it all worked out because it's at the equator, and at the equator, 1 degree equals 60 nautical miles. So at that point, it makes sense both for latitude and for longitude. Each degree will be 60 nautical miles. Now, once you deviate from that, it all changes. But that's what they used to calculate the speed of the Earth, which really was the speed of the sun at the equator going over the flat Earth. So next we're going to be looking at the longitude and time portion of it here. And I found this book called Practical Arithmetic. Highly recommend you guys download this and read it. Very, very good. But there is a section in it, and this thing was published in 1873, and it was put in the New York Public Library in 1904. Let's see here. So let's read this. The equatorial circumference of the Earth is divided into 360 degrees, which are called degrees of longitude. The sun apparently goes around the Earth once in 24 hours. This time is called a day. Hence, the 24 hours, the sun apparently passes over 360 degrees of longitude. And in 1 hour, over 1/24 of 360 degrees is 15 degrees. Since the sun is passing over 15 degrees of longitude requires 1 hour or 60 minutes of time, in 1 minute of time, he will pass over 1/60th of 15 degrees. 15 degrees over 60 is 1/4 equals 15 minutes of longitude. So 1/4 degree equals 15 minutes of longitude. Right. So 15 degrees of longitude require 1 hour of time. 15 minutes of longitude require 1 minute of time. And 15 seconds of longitude require, 15 15 seconds requires 1 second of time. So this is why they have the black and white lines, is between each parallel there's 15 degrees. So the black little square is 5 degrees, 10, 15, and the same for the outer ring as well. But as I stated before, this only matches up to the equator, not out here. Oops. So the 15 degrees marks on the outside ring here only apply when it's on the equator. So let's continue. Hence we see that if the longitude expressed in degrees, minutes, and seconds is divided by 15 equals 3 times 5, the quotients will be hours, minutes, and seconds of time. If time expressed in hours, minutes, and seconds be multiplied by 15 equals 3 times 5, the product will be degrees, minutes, and seconds of longitude. When the sun is on the meridian of any place, it is 12 o'clock or noon at that place. Now, as the sun apparently goes from east to west, at the instant of noon, at one place, it will be past noon for all, let's go to the next page, all places at the east of it, and before noon for all places at the west. Hence, we find the difference of time between two places and know the exact time at one of them. The corresponding time of the other will be found by adding this difference to the given time, if the place be east, or by subtracting it if west. The meridian of the Observatory of Greenwich, London, is the one from which longitude is reckoned. That's right there. Let's zoom in on that. That's the line, prime meridian. Let's see. Longitude is is estimated west 180 degrees and east 180 degrees from the prime meridian. Baltimore is longitude 76 degrees 37 minutes west, and New York is longitude 74 degrees 1 minute west. When it is 12 midnight at Baltimore, what is the time in New York? Well, the analysis comes out to the difference of longitude is 2 degrees 36 minutes and changed to time by dividing by 15 gives 10 minutes 24 seconds. For the difference of time, and as New York is east of Baltimore, the time is later, and we would add. So 12 plus 10 plus 24 equals 12 midnight, 10 minutes, 24 seconds. So 10 minutes, 24 seconds after midnight is the difference in time by using that method. The longitude of New York, okay, so these are some more examples that you can work with down here. But this is the important part. Calculating the time. And this is something that Shills always threw in on my comments. And not just mine, but everybody else's on it. Oops. In order to calculate the time, the degrees and the points on the degrees must be correct. So, therefore, this map with the 360 degrees and the points on there is the actual location of that area. So, New York is right there. Baltimore's just below it, but that is where it is. The shapes of the continents and the shapes of the land masses are correct on an azimuthal equidistant map, because they have to be in order for the time calculator to work. So in order for this calculator here to work, the land masses must be correct. See, this map is actually two things. One, it is an equidistant map. It has the longitude in degrees, and it's also a time calculator. That's where they have all this time on the outside and the degrees marked with the 15 degree intervals at the equator. But what that means is that it would be impossible for this map to work as a time calculator if the land masses did not match the coordinates and the degrees of the 360 degree circle. So, and I'm almost positive I can prove to you, especially when it comes to our friend over here, in which where I'm going to just call them from now on, no longer down under, but on the outer circle. Um, I'm pretty sure I can prove that this landmass is correct, and this one is not. So stay with me here, and I'm going to explain to you how I came about that. But right now, based on all this information I've seen, there is no better map. That's why, as I stated in that video, that tutorial on how to do flat Earth maps, every map you see out there is a version of this. It's a I hate to use that word, the projection, but they hack this one into the rectangular picture, this one right here, and that's where we see all that. That's where it all comes from. So I looked at all sorts of ways to try to calculate the distance or the length of Australia. And I looked at the air routes like everybody else does. And I even had the idea to use Google Street View and start on one end of the country and look at the sign for the mileage and try to add them all up. That didn't last too long. That was tedious. But then I had the idea. I don't know why I never thought of this before, but I would like to introduce to you what could be the key to unlocking Australia, and that is the Indian Pacific Railroad. Now, the great thing about this line, this railroad, this is the southernmost railroad in the world. And it literally goes follows Australia on the southern side from Sydney all the way to Perth. And this is the map they give us on their website on there. But what's interesting is if you look at it on the flat Earth map, it's practically a straight line. So now let's look at some of the stats about this railroad. And this is right from their website. Average length of the train is 704 meters. 2 locomotives and 30 carriages. Now that's very important. 2 locomotives. Keep that in mind. Average weight of train 1,400 tons. Length of track 4,352 kilometers. The length of the journey 65 hours, Sydney to Perth, and 4,352 kilometers. So there's no more track. 4,352 kilometers is all there is. There's no maintenance track. There's no other path. That's all they track, I guess. So, average speed of train, 85 kilometers per hour, with a maximum of 115 kilometers. That equates to about 52 miles per hour for those of us living on the other side. The wedge-tail eagle, Australia's largest bird of prey, I could really care less. Average number of carriages, 30 carriages, including guest carriages, crew quarters, restaurants, lounges, and power vans, whatever those are. So, this data is key to unlocking the distance of Australia. Now, we're going to be looking at the Sydney to Perth route, which has the fewest amount of stops. It could go vice versa, but either one. It goes from Sydney to Adelaide to Perth. Now, I did a quick mapping on Google. I know, but just to see. And Google has a very different distance than the railroad did. And as you can see here, I added it all up. It comes out to 2,331 miles, or 3,751 kilometers, as the total distance for the train ride. So now let's see where it all comes out. So I started off by verifying the actual travel time and looking at their timetables. I was able to figure out the departure and arrival times for each location, and then you just add it up. So it came out that there's a total of 10 hours and 20 minutes of dead time being stopped and 61.74 hours of actual travel time from departure to arrival, and vice versa. So with that, we can then start calculating some variables. So they gave us the average speed of 85 kilometers per hour, or 52.8 miles per hour. And that is for a passenger train. And I didn't put that on here, but anyone can look it up. For passenger train service, it's actually probably a little bit low. But in the United States, Amtrak has certain sections that can go up to 150 miles an hour, and they do it regularly. Apparently, the speed of the train is mostly dictated by the condition or grade of the track or classification of the track itself. So, at any rate, the 52 miles per hour or 85 kilometers, perfectly acceptable, and as an average makes complete sense, because there are sections of the train track that you'll be able to just go wide open throttle. There's nothing there. And trust me, I looked at the southern part of Australia, and with the exception of right outside of Sydney, with the mountain ranges there, everything else is fairly flat. And if you go to the website there for the Indian Pacific Railroad, they actually show you. I mean, it's flat. So I totally believe that is an actual number, and it makes sense to be for about 53 miles per hour or 85 kilometers. So I know that the distance traveled is 61.74 miles total. So all we have to do now is calculate the two. So for kilometers, 85 kilometers per hour times 61.74 hours gives you a total of 5,219 kilometers. In miles, it's 52.8 miles per hour times 61.74. That comes out to 3,260 miles. Okay. Now, for when we compare that against Google, there's a dramatic, and I mean dramatic, difference in the distance of the two. So, and then for Indian Pacific, it's not quite as drastic, but it's still substantial. So for Google, we have a difference of 929 miles, or 1,467 kilometers, difference between the calculation of speed versus distance, or speed versus time, and what Google shows on their map. And for the Indian Pacific, that one, it comes out to 556 miles difference, or 1,467 kilometers. Now, just to give you an example, 556 miles, that would be half of California on a north-south orientation. So it's a big chunk of land. Now, there are those that might claim, well, you know, the track, you have to have, it takes, the track is longer because it's, it has to wind, so the track is actually longer. Listen, there's 52 miles per hour is not only acceptable, but like I said, for a passenger train, probably slightly on the lower side. But on the stats, the train only carries 2 engines. Now, if there was a lot of mountains, they would have 3 engines or more. Okay, as I said before, the majority of the land in the south is all flat. So the average speed and the time it took will tell you, regardless of what the track is, the distance they traveled, if the average speed is, if the train is correct. Now, if the track was truly all winding so much, then the average speed would be lower. Okay, so what I did is I decided to say, all right, well, I'll just calculate it at 10 miles per hour or less. So I put it at 68 kilometers. I recalculated all this, and at 42.8 miles per hour. Now, let me just say this. If you're going on a passenger train in an intercontinental type situation for 3-4 days, and the train's only averaging 42 miles per hour, hop in the car or on a plane. Seriously. Because it's not worth your time. But anyway, so when we do that, we still have a huge difference for Google of 311 miles or 446 kilometers. Now for Indian Pacific, it almost zeroed out. But again, at 42 miles per hour, that's passenger or freight train speeds on a good day. So that's impossible to have a freight train or a passenger train going across a continent that big, and they're only averaging 42 miles per hour. Get out and walk. It'll be faster. So as we look at the actual differences, we have a huge problem here for the globalists. They're going to have to answer this one big time, because Australia is bigger than what the map on the globe or the Mercator projection looks. It matches the flat Earth, the Gleason map. That's what that is. So if anyone can add to this, please add to the comments or contact me through the Google Mail. But I'm fairly confident at this point that Australia is much bigger than it looks on the globe map or the Mercator. And those of you in Australia, if you can hop on a train, take your wife on a birthday surprise or something for 3 days and put an app on your phone to measure the speed. What's your average speed? And if you can do that, it'll tell you what the actual distance is, because we have an opportunity right there, because the track is fixed. They can't change the route of the track. You have one train. You know when it begins, when it ends, at every stop. You can calculate the whole thing out. So I encourage brilliant friends out there, get out there and find out. Hop on that train. Anyway, that's all I've got. Thank you.